Hi everybody and welcome back. We are going to be still talking about finding the area between functions, but we're going to be looking at it from another perspective today. So let's review. Yesterday in class we did this problem. We were finding the area of the region in the first quadrant that is bounded above by y equals the square root of x, below by the x-axis, and bounded by the line y equals x minus 2. If I sketch a picture just to remind us what this looked like, the y equals the square root of x function starts here. It goes through 1, 1 and 4, 2. The y equals x minus 2 function, which I'm going to graph in orange, starts at -2 and goes up 1 over 1 and eventually intersects with my square root function right here at 4, 2. And since the x-axis was another one of my bounds, if I look for the region enclosed by this x-axis, the red and the orange, it was this region of the graph right here. Now, when we actually set this up, what we realized was we needed to set this up using two separate integrals. And the reason we needed two separate integrals is because we always have to look for the top and the bottom function. But when x is equal to 2, the top function and the bottom function of the region we're examining changes. On the left side of that line, the top function is the red and the bottom is the x-axis. And on the right side of the line, the top function is the red and the bottom is the orange. So we weren't able to do this with one integral. We had to actually set up two integrals. The first integral went from 0 to 2. And the top function here was the square root of x minus the bottom was the 0. The second part of this area was the integral from, now we were going to go from 2 to 4. The top function here was the square root of x minus, and the bottom function now was x minus 2. Now, particularly without a calculator, it was a lot of work to kind of go through the process of doing the antiderivatives, evaluating, and finding this area because we had two separate integrals that were required to be successful. So I would say that this problem is challenging because the boundary functions change. Within the interval. So, two separate integrals were required. Today, what we're going to learn is that there's another way of setting up these area problems that can make some of these problems easier. This method involves what we call integrating with respect to y. Now, what I want you to notice about the integrals that we've set up so far, within the integral, the bounds here are both x values. The functions that are on the inside are all using x variables. Which meant that in the equations, y was isolated. and the dx always had an x. When we start to think about things in terms of y, everything that we used to use x values, x variables for, are now going to be things that we use y variables for. So when we set up these integrals, we're going to set them up as the integral from the lower y value, not x anymore, to the higher y value. Inside of the integral, where we used to think to ourselves top minus bottom, now we're going to think to ourselves right minus left. And when we write d, we're not going to write dx, we're going to write dy. Let's go back and do this exact problem, but in terms of y. Now, one way to think about this visually is, and you don't have to do this right now, but just watch my paper. If you rotated this paper like this, now ignore the blue line, but if I rotated the paper like this, instead of, so now I'm putting like the positive x-axis going up. If I think about it like this, if I look at the top and the bottom now, the orange function is always the top of the rotated version of this picture, and the red function is always the bottom. Now, going back to how we draw a graph, that becomes the right function minus the left function, which is why we do right minus left here. How would you set this up? Well, for this same example, and I'm going to sketch a much smaller picture and a much less precise picture because we just went through this whole process. For the same example, instead of thinking about top minus bottom, I'm going to think sideways. So you'll notice I drew my lines going the other direction to help me visualize that. I could integrate from my lower y value, which is 0, to my higher y value, which is 2. Then I could compute right minus left. In this case, the right function would be y equals x minus 2. But I would need to rearrange this so that the y variables are inside. So all I would do is just add the 2 to the other side. And I would put y plus 2 here. Minus, if I now do the left function, and I get x by itself, I would just square both sides, and I would put y squared here. And then I would write dy. The value of this integral is going to be the same as the value here. So let me prove it to you. If we type this in on our calculator, this guy, we would have Math 9, the integral from 0 to 2 of the square root of x dx, plus Math 9, the integral from 2 to 4 of the square root of x minus x minus 2. Oop, I put that all inside the square root. That was my bad. Minus x minus 2 dx. The answer here would be 3.333. Now let's type in this new integral that we set up here. Math 9 from 0 to 2. I would have y plus 2, but your calculator can't type in y's, so you just still type in an x even though you wrote a y on your paper, minus x squared dx. And you'll notice we got 3.333. However, this is a much easier problem because there's only one integral if we had to do this by hand. So let's go ahead. We can actually skip number 1 here. I just did that right here. Let's go ahead and let's try another example. It says here, find the area of the region enclosed by y equals x cubed and x equals y squared minus 2. So let's go ahead and make a really good graph. Now we're going to do this exact same problem twice. One of the times we're going to do this problem with respect to x, and one of the times we're going to do this problem with respect to y. So let's see here. Y equals x cubed. So I know that y equals x cubed goes through 0, 0, 1, 1, and 2, 8, negative 2, negative 8. So y equals x cubed looks like this. Now my next equation is going to be a little bit harder to graph, and the reason it's going to be a little bit harder to graph is because it says x equals y squared minus 2. It's a little harder to graph this because instead of y being isolated, x is isolated. So what I'm going to do as a strategy to figure this out is I'm going to make an xy table. Now, let's choose y values. Normally, we would choose x values and plug them in, but for this equation, we're going to choose y values and plug them in. So I'm going to plug in negative 2, negative 1, 0, 1, and 2. So when y is negative 2, negative 2 squared is 4, minus 2 is 2. Negative 1 squared is 1, minus 2 is 1. Negative 1, sorry. 0 squared is 0, minus 2 is negative 2. 1 squared is 1, minus 1 is negative 1. 2 squared is 4, minus 2 is 2. So I've figured out some points now I can put on my graph. 2, negative 2. Negative 1, negative 1. Negative 2, 0, negative 1, positive 1, 2, 2 again. So it looks like my graph looks like this. Now that means I need to find the area of this region right here. Now the first time we do this, we're going to do this with respect to x. What you'll notice, however, is that on the left side of this intersection point, the top function is the orange function, and the bottom function is also the orange function. And on the right side of this intersection point, the top function is the orange function, and the bottom function is the red function. So finding this area is going to require us to set up two integrals. I'm also going to need to know the x values. This x value is negative 2. This x value is clearly negative 1. But I don't know this x value where they intersect. In order to figure that out, I'm going to go ahead and use my calculator to save myself a little bit of time here. So I'm going to go to y equals, and I'm going to graph x cubed. And I'm going to go to y equals, and I can't graph x equals y squared plus minus 2. So what I'm going to do is I'm going to rearrange this so that y is by itself. So I'm going to have x plus 2 equals y squared, which means y equals plus or minus the square root of x plus 2. What that means is in order to generate this orange graph, you'd have to graph two things: the square root of x plus 2 and the negative square root of x plus 2. Now when I look at my graph, it should look pretty similar to what we've got here on our picture. I'm going to go ahead and calculate this intersection point right over here. And I got x equals 1.215. So in order to find the area with respect to x, I'm going to integrate first from negative 2 to negative 1, and I'm going to do top minus bottom, which in this first region is orange minus orange. The top orange is the positive square root minus the bottom orange is the negative square root dx. Then I'm going to need a second integral that goes from -1 to 1.215. And the top function in this second part of our area is the positive square root of x plus 2 minus the bottom function here would be my x cubed function dx. Now I can go ahead and type that into my calculator. So I've got math 9. Now I typed in the positive square root into y2 and the negative into y3, and I typed in my x cubed into y1. So I'm going to tell my calculator to just recall those things now so I don't have to type the whole thing in. So I'm going to do math 9, integral from -2 to -1. I'm going to recall and I'm going to use y2 minus, I'm going to recall and I'm going to use y3 plus, I'm going to do math 9 from -1 to 1.215. I'm going to do recall and I'm going to use y2 minus, I'm going to go to recall and I'm going to use y1 dx. So again, I only had to type in the equations once, I could just recall them now. And I got 4.215. Now, is that impossible? No, but it is a little tedious. Let's think about doing the same problem, but now we're going to do this problem with respect to y. If I sketch the same picture, and I'm not going to be quite as precise this time because we kind of know what it looks like now. We've got this guy, we've got this guy, and we've got this guy. If I think about this with respect to y, then instead of thinking about top and bottom, I'm going to be thinking about this right minus left. Now if I rotate my picture so I can get a better visual, the red function is always the top. In other words, that's the right. And the orange function is always the left, the bottom. So here I'm going to label my right is y equals x cubed, and my left is x equals y squared minus 2. And the nice thing is that that never changes. We don't have this same issue we saw here where the top and the bottom switched and now they had a different top and bottom for the second part of the area. So what we can do is set this up with one integral. Now to set up this integral, we're going to need to know the y values. This y value is -1. This y value, if I go back to my intersection point on my graph, now I care about the y values, which the y value here would be 1.793. So I would integrate from -1 to 1.793. Instead of doing top minus bottom, I would be doing right minus left. However, you can't put an x inside of an integral if you're doing right minus left. You need to have a y. So what I'm going to have to do is cube root both sides here to get x by itself. Minus, now I can do the left, already has a y in the equation. It was already arranged the right way from the beginning. And I'm going to write dy because I'm doing everything in terms of y. Y values, y variables, dy. Now, I'm going to type this in. So, -1 to 1.793. Now remember, even though this says y, you're just going to type in x's on your calculator and that's okay. So to type in cube root, you can go to math, and the third thing is cube root, minus x squared minus 2 dx, and I got 4.215. You'll notice this answer and this answer are exactly the same. It's just two different ways of getting at the same thing. All right, the big idea today is that sometimes instead of doing things with respect to x, we can do them with respect to y, which means instead of thinking top minus bottom, we think right minus left, and we use y values for our bounds. And all of our equations need to have y's in them. We will go over problem 3 tomorrow in class. Thank you guys so much for watching and have a great afternoon.